Greetings, mathophiles, and welcome to a video in which we'll demonstrate how to work a couple of examples involving the first derivative test. You'll see the theorem that lays out the first derivative test on your screen. Long story short, if I have a function at a place where it's continuous, its derivative is either 0 or undefined, and the derivative is changing sign negative to positive, then the function must be having a minimum. If the order of the sign change is reversed, the function must be having a maximum. And if there is no sign change in the derivative, then there is neither a maximum nor a minimum. Our first example is a very traditional one in which you might be given a function defined by some equation and be asked to find the locations of all the relative maxima and minima. And our function is g of x equals x squared e to the x. And if we're going to locate maxima and minima using the first derivative test, we of course need the first derivative. And since this is a product, we will use the product rule. So I have the first factor, which is x squared, times the derivative of the second factor, which is e to the op x, times -1. That's a tiny little piece of chain rule that is easily missed. And then second factor, e to the op x, times the derivative of the first, which is 2x. We can factor out an x and an e to the op x, and we are left here with an op x and here with a 2, so we could maybe call this 2 minus x or op x plus 2, either way. It's a good idea to make sign charts to help you sort of organize all the information that you need to keep straight. And it's also a good idea to have a sign chart for the original function rather than just for the first derivative, because it will tell you at a glance, for example, whether your function is discontinuous someplace. And if your function is discontinuous someplace, it sort of doesn't matter what the derivative is doing. You're not going to be able to use the first derivative test in order to locate maxes and mins. So my original function, my g, is 0 at x equals 0 and positive everywhere else. So actually, even if you didn't know any calculus, you would be able to say that there was a minimum at x equals 0, because if I'm 0 here and positive everywhere else, this must be a minimum. It actually must be the absolute minimum for this function. If we take a look at the derivative, it's going to be 0 at x equals 0. It's going to be 0 at x equals 2. And if you either check test points on these intervals or maybe use some other clever methods that are potentially at your disposal, what you find is that the signs on these intervals look like this. And now you have enough information to locate the relative maxes and mins. I have a place at x equals 0 where the original function is continuous. It's continuous everywhere. And first derivative is 0, but changing sign negative to positive, that will have to be a minimum of the original function g. And at x equals 2, g prime is 0, but changing from positive on the left to negative on the right. And that confirms that we have a maximum there. And should there be any doubt, we can try to get it in the screen here. We can take a look at a graph of this function. Sorry about the glare. And we do in fact see that it has a minimum at x equals 0 and a maximum at x equals 2. That's a very traditional sort of example. Our second example is of a type that the AP Calculus Exam Development Committee just loves. They give you the graph of the derivative of some function, and they ask you a bunch of questions about the function itself. And for our purposes in this video, we're interested in the question of relative max and relative minimum values for this function. So we have some function f that is continuous on closed -5, 4. We have a graph of its derivative here, and we might be asked the question on the open interval, -5 to 4, what are the critical values? And once we have those critical values, which of them represent maximum values of f, which represent minimum values of f, and which are neither a maximum nor a minimum? And at the very end, we'll take a look at what might be going on at the endpoints. So, keeping the first derivative test in mind, all we really need to do is look on open -5 to 4 for any place where f prime is either 0 or undefined. It's never undefined. It's 0 in 3 places, at x equals -4, at x equals -2, and at x equals +3. Now, at x equals -4, f prime is changing sign from positive to negative, which means f is transitioning from increasing to decreasing, which means it's having a relative maximum. At x equals -2, f prime is changing from negative to positive, which means f is transitioning from decreasing to increasing, which means f is having a min. And at x equals 3, there's no sign change in f prime, which means there is neither a max or a min of f. Not too tough, folks. Now, what about the endpoints? What's going on at x equals 4, for example? Well, since f prime is positive, f is increasing to the left of 4. And so if f is increasing on its way into that endpoint, then at that endpoint, f must be having a relative max. So there's a relative max at x equals 4. This is not an instance of the first derivative test. This is just us reasoning our way through what's going on at the endpoints. And then over at -5, f prime is again positive. And so coming out of whatever the value of f of -5 is, f begins to immediately increase, in which case it must have been rising, so to speak, out of some kind of minimum value. So f must be having a relative minimum at x equals -5. Now, as a practical matter, when you're answering test questions, it's good to pay attention to whether you're being asked to locate maximum and minimum values on the open interval or the closed interval. If you're asked to look on the closed interval, then you have to bring in this kind of reasoning about what's going on at the endpoints of the interval. If you're just asked about the open interval, it's straight up first derivative test. I hope this has been helpful. Happy mathing.